Okay, so last time we looked at the closest pair problem. We saw two ways to solve it. The first was this grid-based method, right, which was pretty fast. And then we got a little bit into this concept of a well-separated pair decomposition. So the well-separated pair decomposition has a bunch of applications. We touched on them, very, very briefly at the end of the class. And so what I'm going to do today is talk a little bit more about how this whole machinery works, right? So the subject of today's lecture is the well-separated pair decomposition. And at a high level, we know we can solve things like the closest pair of points using this. We can find like the k closest pairs, all nearest neighbors, and it's also useful for a bunch of geometric approximations, so you can use it to find things like spanning trees, compute the diameter of a point set, and also for speeding up n-body simulations approximately. So it has a bunch of interesting applications. It's usually used to get these sort of subquadratic algorithms for processing huge sets of points, right? So it's a really interesting kind of technique, right? I mean, I think it's a very clever data structure anyway. It's something like some weird piece of computation from like a different dimension or something, right? It's very much unlike any of the other things we're looking at. But okay, so let's go through the definition here again. So let P be some collection of points, right? We'll label them with subscripts. And again, there's going to be n of them. And these points will live in RD or affine space, or however you want to do it. And we're going to require them to be distinct. Otherwise, this isn't a well-defined construction. OK. And so we're going to say that an S well-separated pair decomposition, right, which I'm going to abbreviate with WSPD for the rest of this lecture, is basically a collection of pairs of subsets, right? So this is a collection of pairs of sets. We'll write these as basically AI. Right? Which have the following properties. So the first is that, I guess the 0 with 1 is the types of these things have to be consistent. So each AI BI is going to be contained in P. 2, or I guess the sort of second easy property, is that we're going to require their intersections are disjoint. Right? By the way, these properties are not all independent, right? So some of them imply one another. So the intersection of AI and BI better be empty, right? So these are all pairwise disjoint sets. And if we take the distance between any pair of sets, right? So we'll write this as the distance between AI and BI. This better be greater than or equal to S times the max of the diameter of A, or the diameter of B. As an aside here, right, just to quickly recap this point, we should remember that the diameter of a set S is the maximum of all PQ in S of the distance P minus Q. So it's basically you find the farthest pair of points in the set S, that's the diameter, right? So straightforward. And the distance, again, between two disjoint sets here, ST, this is just the minimum of P and S q in T of P minus Q. All right, so we're going to keep using this notation here. It's pretty straightforward, right? And then the final point is that if we take the union from I equals 0 to R of, and I'm going to write this a little bit funny here, but I'll explain what this means in a moment, of this sort of fancy circle Cartesian product of the two sets, it better be equal to this set P. What do I mean by the fancy Cartesian product with the circle there? I just mean that this is the unordered Cartesian product. So that's what this is. Don't want to spend too much time on it. It's not a very important idea. But it's just because if you take the normal Cartesian product of two sets, right? So if you take, say, like, A cross B, this will give you the set of all pairs, A, B. But we don't care about the order of these pairs. So if we take A and then do this fancy circle with B, this will basically give us AB and BA. So another way of thinking about it is that if we write S, circle Cartesian product with T, this is just S cross T union T cross S, right? Just because we want to, keep track of the fact that these things aren't ordered, right? So it's sort of like a commutative Cartesian product, or however you want to call it. OK, not too important, but just don't want to confuse anyone with that. OK, and so this is a well-separated pair decomposition. I mean, I could have actually used the fact that the points are all distinct with this axiom here to eliminate this point number 1. But it's useful to remember that these things are disjoint sets, right? So we can't ever, put 2 points into the same thing or, have them inside there. So the basic idea is that a well-separated pair decomposition takes all of the n² possible interactions between every pair of points and then splits them up into a bunch of tinier subsets, right? So we have these sort of clusters of points. And then we're going to look at the interactions between these clusters. So sort of a picture, you can imagine that we have a point set. Maybe we have a cluster here, another cluster here. Then in a well-separated pair decomposition, we group these two clusters together and separate them by some axis here, right? And so this has to have the property that, so suppose this one is AI, this is BI, right? Then this distance here is basically the distance between AI and BI. And we know from the second condition right here that this is greater than or equal to S times the maximum diameter of the 2 points. And yesterday, we proved the following sort of simple or easy little result here, right? Which is that if I take any pair of points here, so call this one P and this one Q, right? And if I take another pair of points, maybe call this one P prime, this one Q prime, then if these two things are indeed S well separated, then I can say something about the distance between P and Q in terms of the distance of P prime and Q prime, which is that we have the following sort of easy theorem. All right. And in some sense, this is sort of like the fundamental property of what makes a well-separated pair decomposition tick. That the distance between P prime and Q prime is less than or equal to 1 plus 4 over S times the distance between P and Q. All right. So, OK, that's a recap of what we went over last time. So any quick questions about that? All good so far? All right, so that's the idea. So what we're going to talk about today is basically how we compute one of these things, right? And then we're going to see how we can concretely use it to then solve some interesting problems. So one easy thing that we also remember, too, is that from last time, we know that if the closest pair of points are contained, or that the closest pair of points have to be contained inside separate pairs in the well-separated pair decomposition. So a direct consequence of this theorem is that if PQ is the closest pair in P, then this set PQ is in this well-separated pair decomposition W. And it actually has to be at least a 2 well-separated pair decomposition for this to work. All right. So that's the basic idea. OK. So we have this thing. It's pretty cool. We can use it to do this sort of approximate n-body stuff. Let's look at how to build one. All right. So there are a couple of different ways that we can do this. The one that I'm going to show you right now is not actually the most efficient way to do it, right? But we will see soon that it can be made more efficient. So I'll start out by explaining sort of like an overview of what we're going to do. So I'm going to erase all of this. All right. So the first sort of approach to building a well-separated pair decomposition uses this technique called a fair, or this data structure called a fair split tree. All right. So, OK. So the first way to do this is we're going to build these with fair split trees. So we'll see first how to build fair split trees in a very naive, somewhat slow way. There is a very fast way to do this, right, which I'm not going to cover because it's extremely complicated. And then we'll see a sort of alternative to fair split trees in the second part of this lecture, which is not quite as good as the really fast way to build fair split trees, but it's sort of like the industrial grade, kind of like somewhat crappier, a little rougher, but it's easy to implement, right? So we'll see the easy sort of algorithm to do it. The easiest algorithm is actually the one that I'm going to start with right here, right? So we'll start with the very easiest, but it's a little too slow, right? But OK. Well, let me just say how this works, right? And then we'll kind of go, refine it over time. So OK, fair split trees. They're structurally the same thing as KD trees. So it's sort of what do I mean by that, right? Which is that they basically have the same data structure. So they're the same properties as a KD tree. So each of these things is going to be built as a set of axis splits along different axes over here. But the invariants of them are going to be different. So the first key difference, right? So the differences are invariants change. So in a KD tree, if you recall, we basically start with a point set, and then we keep recursively splitting along a different axis that we're going to cycle through. Here, instead of splitting through some axis that we're going to just cycle through each time we go through the like one level of the tree, we're going to always split along the largest axis. So the first difference is that we split along the longest axis instead of cycling. All right. And the second point is that instead of splitting at the median, which would basically cut our point set into 2 equal halves, we're going to split at the mean. The consequence of this is that our trees will no longer be balanced. So they could be extremely lopsided, like practically a linked list. But that's OK, right? That's the basic idea. If we wanted to construct one of these things, there's a really sort of simple procedure that we could use, which is we can just recursively find this longest axis, right? And we're going to basically assume that it's going to be axis aligned. So the way we do this is we construct a bounding rectangle over our point set. We find whichever is sort of the longest or the highest aspect ratio length, cut that in half, split the point sets, and then recurse, right? So that's sort of the sort of slow algorithm for building a fair split tree. All right, and so the input here will be some collection of points. We'll just write that as P. We'll start out by constructing a bounding box. So we'll just suppose that we have two vectors, low and high, which are the bounding box of P, right? That's easy to do. You just scan through the points, keep track of the low and high values. Let D here, actually, I probably don't want to use that. I already have D. Let's call it J, right? So let J be the longest axis of box, right? So this box that we just calculated here. And we're going to define M to be the mean of these points, right? So it's basically going to be sort of this midpoint of this box, right? I guess I shouldn't say split at the mean, right? But sort of split at the middle is maybe the right way to middle, right? So this is basically halfway between the upper and lower bounds, right? So we're going to set M equal to low j plus high sub j, then divided by 2. All right? And then we're just going to return a tree. That's it. So we'll just take this thing, we'll return a sort of KD tree node, right? It's the same data type as a KD tree. So we'll keep track of the axis, which is going to be j in this case. The left subtree will be a recursively constructed tree, so we'll call a slow fair split on the set of all P in P, where P sub j is less than or equal to M. And we'll do this again to the right side. So we'll call recursively slow fair split of the set of all P in P, where P sub j is greater than M. And that would do it, right? So the obvious problem with this algorithm is that it could take quadratic time. Don't worry about that for now. There are ways that you can build fair split trees in n log n, all right? We're not going to talk about that, but just suppose that you could build one in n log n time. This algorithm would be good enough to do it in quadratic time, okay? We will later on see an alternative that we'll be able to build in not quite n log n, but almost good enough, right? Okay. So that's the first point. Let's draw a picture of this whole thing. So make a figure here. So suppose I have some set of points.
You say low high, doesn't that not really make sense for more than 2 dimensions?
It's basically, you can think of this as storing a vector, right? So this would be the upper left corner of the box, right? And this would be the lower right corner. So this is basically just the components of this vector are the lower values, right? And then this is the max value. So this is just the array of all the min x value, or all the min components, max components. All right, so it's, that works in any dimension, no deal, or no big deal. All right, this can be generalized to any dimension, right? But there is going to be sort of an exponent here that will be exponential in D, which causes it to not work in high dimensions. But in 2 or 3, it's good enough. So okay, so let's do this. So the starting point here is we're going to go build our bounding box around this point set, right? Which is easy enough to do. So this will be our first node here. And then we'll take this point set, and I guess we'll just cut it right down here, because that looks like the middle. All right. And then we're going to split the points into 2 separate halves. So again, we'll go through here for each subpoint. I guess I'm going to do the next level of the tree in a different color. How about green? So we'll recursively go down through this. Similarly for this level here. Right, and then in each of these nodes, we have to cut it right in the middle. here. Then we'll go down one more level in each of these two subtrees. So I guess this one. Just go here. That's a leaf node, so that's done. Then I guess this one we have to cut here. This one, I suppose we can cut it here. This one will cut in there. And maybe like one last level of this. So I guess we'll get down to here. That would get cut there. OK, so let's draw what that tree would look like. I'm going to erase the algorithm and then just draw what the tree is.
It's kind of like a smarter quad tree.
Yeah, exactly what it is, right? We'll see a dumb way to build it using quad trees, actually, but that's OK. This is the original way you do this, though. So, all right. So, OK, so what does this look like? So we start out with our root node here. So let me number all of these things. So we'll call this point 1, 2, 3, 4, 5, 6, 7, 8, 9. OK. So we start by splitting this thing in the middle at that point here. So that's for this side. Then on the left side of the tree, split here. All right, so we'll go basically on convention, say this is the left side for this. So I should probably like draw maybe some like arrow here to like label the nodes of the tree. All right. Yeah. All right. Well, I'm just going to draw sort of the structure of the tree, and then you can kind of see what it looks like. So this would be node 2, node 1, node 3. So the values will all be stored in the leaves, and then the intermediate nodes of this tree are splits. Each split keeps track of, in a sense, it's sort of split axis and rectangle. Right? And then it would really be enough for it to just track the rectangle for each node for our purposes. So yeah, and then on this side over here, I guess now I have 4, 5, 6. Then I have some root here. So we'll call that one 9, 7, 8. All right. Now, there's no guarantee that these trees have to be balanced in any way, shape, or form. You know, if we just take some random set of points, we're probably going to get a pretty random-looking tree. If you want to construct a really unbalanced fair split tree, though, all you have to do is just distribute your points on sort of like a log scale, right? So if I take like a point here, call this point 1. All right, let me just draw like an interval, right? So here's sort of like how to build an unbalanced. I'll write this as basically unbalanced tree. So we'll put our first point here. So put a point at 1, put another point at 1/2, put another point at 1/4, put another point at 1/8, so on, down to 1/16, etc. So if you build something like this, right, then when you construct a fair split tree, you're going to have to first split them at the middle, then split them at the middle, then split them at the middle, and every time you do this, you're going to add another like layer onto the tree, right? So we shouldn't think of these things as being balanced, but that's OK, because we're not going to be using these trees for searching. We're actually going to be using them to sort of pre-process our point set. So then we can take this tree and then build a well-separated pair decomposition out of it. So the basic idea is that the nodes in this tree are going to correspond to clusters that will ultimately become pairs in our well-separated pair decomposition. So we're just building this tree to sort of, warm up our point set, right, and just chop them up into these tiny little clusters. And then they will basically form the pieces of the final well-separated pair decomposition. So that's the high-level idea for how that works. OK, so how do we turn one of these trees into a well-separated pair decomposition? Well, the algorithm for doing it is actually kind of the obvious thing. Like, there's really only one way to sort of do it. And we'll just walk through it right now. So it's like you basically just start from sort of like the root node of this tree, and you just keep splitting them apart. And eventually, this will produce a well-separated pair decomposition. But let's be more specific. So, OK, is everyone good with this right now? Oh, yeah. Actually, no, wait. There's one other thing I need to say about this, too, which is that if we take any two nodes inside this tree, there's a couple of things that we can say about them that will actually be important later on. I want to draw some attention to them right now so that they're in mind while I still have this figure on the board. One is that the rectangles for any two nodes are disjoint. Right? So if I take like this node here, this would correspond to this rectangle on the board. No other rectangle other than the leaves of this tree will intersect it. So any pair of rectangles are disjoint. And if I take one of these rectangles and draw a ball around it, right? So if I take like this rectangle here, draw a ball that's basically like the minimal bounding ball for that rectangle, and I draw another bounding ball between another rectangle here, then the amount of overlap between these two balls is going to be proportional to the radius. So I can't like completely stick, two disjoint trees into one another. So they're always like sufficiently pushed apart. Right? That's sort of an intuitive idea. We'll come back to that, and we'll use that later. But that's the key thing, right? That these things are all kind of pushed apart, and that their bounding balls aren't too intersecting, right? So that's the reason that this is important. OK, so that's fair split trees. Now we'll go through the process of turning a fair split tree into a well-separated pair decomposition. So supposing you've built one of these things, from there, it's all easy, right? So the hard part is actually building that fair split tree in the first place, right? But we're going to just take it for granted right now that you can do that. All right. I mean, maybe you went through and you read Callahan and Kosaraju's paper where they described this technique and invented well-separated pair decompositions, and you implemented that. Or maybe you will kind of skip ahead and then implement the thing that we'll talk about later. But you got something that's basically a fair split tree. So here is now how we go from a fair split tree into an S well-separated pair decomposition. And we're going to use the following algorithm, which we'll just call build WSPD. The input to this algorithm is a pair of nodes in the fair split tree. So we're going to require that U, V are nodes in the fair split tree. Also, by some abusive notation, we will identify a node in the fair split tree with all of the points in that node, right? So we're going to identify nodes in the fair split tree with all points in the node. So basically, it's like you just start from some node in the tree, you walk all the way down to the leaves, you take all of those points in the leaves, that's the point content of that thing, right? So we're just going to use these two terms interchangeably. If we want to talk about it as a point, or as like a node in the tree, we'll treat it as a node in the tree. Otherwise, we're just going to treat it as a blob of points. All right. So here's the algorithm. So the first easy case is that if U or V is a leaf, or we'll actually say if U and V are leaves, not or. So if they're both leaves, then we're just going to return this pair UV, right? And so this is basically why I wanted to make this identification, because now I can basically return pairs of nodes instead of pairs of point sets. So I don't have to like march through the tree to construct one of these pairs, right? The second thing is that we have to make some comparison about their diameters, right? So without loss of generality, we'd like to assume that U is the larger. So if the diameter of U is less than the diameter of V, then we're just going to swap U and V. All right, so that's just to simplify the number of cases that we have to worry about. So now, here's what we do, right? We say, if these are actually a well-separated pair, so that is, if S times the diameter of U is less than or equal to the distance between U and V, then we're going to return UV. Right? So that's easy. Right? So basically, if we've gotten to a well-separated pair at this point, we're done. We'll stop the recursion. Otherwise, actually, I'm going to just return sort of a set of pairs, right? Because I want to return a well-separated pair decomposition. Otherwise, and this is sort of the recursive case, is that we're going to call this function twice. We'll call build WSPD with the left child of U and V, and then unite that with build WSPD with the right child of U. So just recurse. So that's the basic algorithm. Right. And then to initialize this is we basically call build WSPD with the root twice. OK, and that'll do it. So we basically run that procedure. When everything is said and done and all the smoke clears, we will be left with a S well-separated pair decomposition, I claim. That's actually not so hard to see, right? Because what we're always going to spit out here are pairs. And at some point, we're going to eventually visit every single node inside the set. So we know that if something is returned, right, it's going to be stored inside one of these well-separated pairs. And we will for sure hit every pair of nodes, or cover every pair of nodes in the worst case. So this is OK, right? This is not a big deal. And it will produce, the expected well-separated pair decomposition as a result. Actually, I think it should be left of root, left of right of root. I may need to double check that. I think that's correct, though, something like that. OK. Anyway, so that's the idea, right? So it's going to basically compare every node. No, it's with the root twice, right? It is with the root twice. Yeah. So, OK. So the sort of trivial proof, right? I'm not even going to spend too much time on it, is that the output is, in fact, an S well-separated pair decomposition, right? That's easy, not very exciting. The harder thing is to argue that the output from this algorithm is actually order n, right? That's the trick. So the fact that we built a well-separated pair decomposition is somewhat boring, but the neat thing is that this algorithm will actually build a relatively small well-separated pair decomposition. And the reason that that is true has to do with the details of the fair split tree. So that's the hard thing that we're going to try to prove. So where should I make space here?
Quick question.
Yeah.
So, well-separated pair decomposition, it's pairs of sets, right?
Yes.
It looks like we're returning just...
Remember this point here, right? We are returning nodes in the fair split tree, but we're identifying them with sets, right? So we're going to represent these sets of points by nodes in the fair split tree, right? That's why we're returning pairs of nodes. So what you do is if you get one of these nodes inside a pair, you just traverse that whole tree. That's the set of points. You could do that in linear time. It's no big deal to recover all of the points from a node in the tree. All right, so that's...
So that really only applies to that third if then, because the first if is single nodes, single points.
Yeah, exactly. So that's OK, because we're going to return them. And then in this one, this is where we would actually return a well-separated pair. So the key thing is that in each of these cases, we're always returning well-separated pairs, right? So this will always return an S well-separated pair decomposition, and every pair of nodes will eventually get visited in the tree. So that's no big deal, right? It will create an S well-separated pair decomposition. That much is certain. What is not as certain is that it's going to be some relatively small well-separated pair decomposition. And this is the really hard thing to prove. And I'm going to give you a sort of sketch of how this works, trying to capture the intuitive essence of this without getting too bogged down into the details. But this is what I'm going to talk about now. So I'm going to keep this algorithm on the board here, because I would like to refer to it. And I am now going to try to use this space here on the board to try to explain how this works or what's going on. So I guess I'll kind of move the union there. All right, so that's the algorithm. Here's what we would like to prove. The proposition is that the size of the output of that algorithm is order s to the d times n. And that also means that the running time of the algorithm is order s to the d times n, because it's just linear in the number of nodes which are generated, right? So this is what we would like to prove. So to do this, let's consider how many times we get to this line, right? So this is basically the case where we return a pair. So we can, or we could also kind of group this point and this point together here too, because basically if these two things are leaves, then one of them is going to be a well-separated pair. So in a sense, we could actually like do without this line, really. This is actually not even like necessary. It's just sort of a clarifying thing. So, OK. So really, we only have to worry about when we get to this point. So by convention, let's define parent of some node in the tree u to be equal to the parent of this node, right? So the parent node in the fair split tree, right? So we basically go up a level, all right? We wouldn't actually need them when we're computing anything, but for proving stuff, we'll need to refer to it. And so consider when we get to this point, right? Then because we had to split one of these nodes, right? So basically, if the diameter of u was larger than the diameter of v, right? So we got to this point. And actually, let me sort of swap the order here, right? We'll put v first and then u. It's just because I wrote my notes with v first in this case, right? So if we ever get to this line, then it was because in the previous iteration of this loop, v was split, right, into its left and right children, and it was recursed. So if a pair uv was generated, then in the previous iteration, u parent v split into uv. Right? So this is the thing. So we started at some like level of the tree, right? And then we split it apart, and then we got to like this sort of tinier node here. So let me draw a picture of what's going on. So imagine here we have our two nodes. We'll call this one v, and this one u. Right? And so we're going to represent the point sets here by some ball. All right? Previously, we had this node here, which we'll call parent of v. Right? And so parent of v and u were not well separated. Right? That is, this condition failed. And so we had to split v apart into tinier pieces, and then we got down to v. So what we would like to show is that the number of times we ever had to split apart parent of v is no more than order s to the d. All right? And if that is true for every node in the tree, that it was never split more than order s to the d times, then the total number of nodes in our resulting or the total number of pairs is order s to the d times n, all right? Because no node could ever split apart more than s to the d times, right? And so we can just look at for each leaf node or each pair that was generated, how many times the parent directly above it had to be split. Okay, so what can we say about this situation? Well, there's a few things that we know, right? I mean, this is just because it's a well-separated pair decomposition. But to do this, it will be helpful to bring in U to the picture. So suppose that we've split the parent of V, right? Well, then we also know that U here has its own parent, right? Somewhere over here. This is the parent of U. And we know a few things about parent of V, which is that it has to be somewhere in between parent of, so the diameter of parent of V has to be strictly larger than U in order for it to have been split. But it has to also have been less than parent of U in order for parent of U to have eventually split into U. So we know that the diameter of U is less than or equal to the diameter of parent of V, which is less than or equal to the diameter of parent of U. All right, so we have this sort of ordering over here. So parent of U is larger than parent of V. Parent of V is larger than U. All right, that's the sort of configuration that we have. So because these things were not well separated at whatever level they were at, this means that the distance between U and parent of V is less than or equal to s times the diameter of parent of U. Or the diameter of parent of V. Diameter of parent of V, not diameter of parent of U. Right. OK. Yeah, this just means that they weren't well separated, so this conditional didn't fire. Right. So we basically got down to this level. So in order to have split them, this had to have been true. Similarly, the distance between parent of U and parent of V has to be less than or equal to the distance between U and parent of V times 1 plus 4 over s by that basic property. Right? So this it's not then a less than or equal to, but it should actually just be a less than. It's not less than or equal to. So this has to be less than 1 plus 4 over s d U parent V. That's because U is contained inside parent of U, right? And so using that theorem that we wrote and I erased, this has to be true, right? Because it's just the contrapositive, it's the dual of that theorem. Another way that we can say this, though, is that this has to be less than s plus 4 times the diameter of parent of V by basically a substitution, so combining these two results. So this whole thing is less than s plus 4 times the diameter of parent of V. OK. So what does this mean, right? Well, it means that this parent of U here has to be contained inside some ball of radius s times the diameter of parent of V. Right? So I need some more space. I'm going to erase some things here. So this is sort of the tricky thing. So here's kind of a picture of what's going on. I'm going to erase this algorithm. I think we got the idea for what's going on there. So here is a picture. This is parent of V. Farther out, we have this big ball, not drawn to scale, right? This thing here has a diameter, right? Or a radius, which is s times the diameter of parent of V. And we have this other ball here, right? I guess I'll just draw it off to the side here. This would be parent of U. And so this parent of u has to be somewhere contained inside this ball, right? So it's got to basically cover like this chunk of this ball. So now here is the trick. How many possible parent u's could there be that we could pack into this ball? Because we know that each of these two things, they can only overlap up to like half of their radius, right? So the question then is, if we take this parent u, how many of them can we pack into there? And we know a couple of things, right? If we want to pack it as tightly as possible, we would like to minimize the radius of parent of u. But the radius of parent of u has to be at least the radius of parent of v by this observation here. So here is sort of the question, right? Given a sphere with radius, I'm just going to write this at order of s times the diameter of parent of v, how many spheres with radius at least order of the diameter of parent of v can we stuff into it? Right. So this is just the question of how many nodes in the worst possible case can get close enough to parent of v such that if I split them one level, then this guy will split at the next step, and then I will basically have to return that well-separated pair. Right. So in order for parent of v to split, I have to basically stick this thing in this ball here somewhere. Right. That's a guaranteed fact. So how many of these things can I stick inside there? The answer to this question is s to the d, right? Because you can think of this as something like, if we kind of smeared this out and approximated it as like boxes, right? How many boxes can I pack into this space, right? If I have a box with a side length of s, then the number of boxes that I can fit into it in d dimensions is order s to the d. It's basically the same thing here. The constants involved are messier, right? They're actually smaller, but it will end up being order s to the d. In an asymptotic approximate sense. There are a lot of weird constants involved, but we don't care, right? We just want to figure out how many of these balls we could possibly fit into it as where s and d are two free variables, right? We're not worrying about like the specific details of it. In practice, it will probably be a lot smaller than s to the d, right? But this is the upper bound. So you can't fit more than s to the d of these balls in there. So feeding it all the way back, this means that whenever we get to one of these configurations, if we look at parent of v, the number of times parent of v can split and then create a node is at most order s to the d. So therefore, the size of the well-separated pair decomposition is order n times s to the d in the worst case. All right? So that's the sort of conclusion. So the conclusion of all of this mess, right, is that we can prove that the well-separated pair decomposition will turn into something that's, at most size n, right, with this exponential parameter in s, right, with n d. So that's the idea. So any questions about that? I mean, I didn't prove this sort of packing result, but you can take my word for it, right? It's fairly clear that that should be about right. It's order s to the d, right? Sort of if you think of like the radius of a sphere, right? The volume grows as like the function of s, right? So, okay. Any questions here? No. Okay, good. So that's the conclusion. So the basic upshot of this is that if we use this fair split tree thing, we will be able to build well-separated pair decompositions that aren't too large. Right? So I'll just summarize this. Here's the sort of result. The build WSPD, or I'll actually write it this way. I'll say an S WSPD on a set of points P can be built in order construction time for that fair split tree, which you can do in order n log n. I'll explain later about that. This is sort of the tricky thing there. Plus the size of this resulting fair split tree, so the cost of running that algorithm, which is s to the d times n. So we can build this thing in n log n plus s to the dn, and is of size at most order s to the dn. All right, so that's the result. You make s bigger, you'll get more nodes, but it'll only grow, linearly in n. That's the key thing. All right, great. So, how am I for time right now? What time is it? 10 to 2. OK. All right, then I'm going to skip a couple of proofs because I want to get to some other stuff. So let's now say how we can use this thing to solve two important problems. So, OK. So the first thing we're going to look at are k nearest neighbors. All right. So k nearest neighbors. This is kind of like the closest pair of points problem. It's just we want to find the top, k closest pairs. So we want to find the k closest pairs. It turns out we can solve this in order n log n plus r plus 4 to the d n plus k by building a four-separated, well-separated pair decomposition. So just an order 4 well-separated pair decomposition. Here's how we do it, which for k substantially less than n squared, this is a pretty good improvement, right? So if k is like less than n squared points, we'll get there pretty quick. So here's the first point. So we'll write in step 0. So step 0 is compute a 4 well-separated pair decomposition. That's the hard part, but we already saw how to do that. And we're also going to say sort pairs by separation distance, which we'll need for this thing, right? So that's also an order. This would just be an order n log. All right, or we'll basically, we have this extra parameter in there, but we don't have to worry about that, right? So build the well-separated pair decomposition, sort it. OK. 2. So we're going to assume that once we've built these things, that we now have the sequence, A0, A1, or A0, B0, right? A1, B1, etc., such that the distance AI BI is less than or equal to the distance of AI plus 1, BI plus 1, right? So that's the notation that we're going to use. We're going back to the AI's BI's here, right? So, OK. Compute the smallest L such that the sum from I equal 1 to L. So we're going to sum up the first L pairs in this sorted list of the cardinality of AI times the cardinality of BI. So we're going to sum up the size, the number of pairs contained in the first L elements, is greater than or equal to k. You could do this, just through a simple brute force linear scan, because calculating these two sizes is like a constant time operation. So that's the idea. So this is basically counting the number of pairs inside, or the number of pairs if we compute all the interactions that are represented by each of these well-separated pairs. So 2, after you've done this, set r equal to the distance of A sub L, B sub L. All right. OK. And now that we've done that, we're going to then compute another parameter. So we're going to find, or I want to say find the largest L prime such that D of A L prime B of L prime is less than or equal to 2 times R. So we're going to find the largest pair now, which is over there. So the idea here is that we first started out with, like, say some collection of pairs. This has k interactions in it. The distance here is L. We'll basically go out to this. We have this distance here, which is R. We're now going to go out to this range 2R. All right. Now that we've done that, search all interactions. So you're going to find all pairs in A0, B0, etc., all the way up to AL prime, BL prime. Return k smallest pairs. That's it. OK. So that this algorithm is correct is, again, pretty easy to verify. Right? This is basically because the distance between any of these pairs, right, is going to be bounded. Right? Now that we've basically constructed this first k here, right? So we can basically look at this distance here. And so if there are any ones which are closer than these first k pairs, they're going to have to be stored in here. And so that will be covered, right? So this is sufficient to basically cover the correctness of the algorithm. The hard part is to show that this thing runs in order k extra time here. And this hinges on another kind of subtle packing argument that I'm not going to go into right now. But suffice to say that you can show that the number of elements in this range is not much larger than k, right? So the total number of pairs which have to be considered when you're doing this ends up being order k. All right, so this algorithm will get you the k closest pairs in pretty much whatever it takes you to construct the well-separated pair decomposition time. OK, so that's pretty neat.
Why is 4 arbitrarily chosen?
The reason is that if you remember that inequality, we want to get it to 2. Right? We had this thing where basically like the D, remember this theorem, P prime minus Q prime is less than or equal to 1 plus 4 over S. We basically pick that S equal 4. That's also where this 2 comes from, right? This theorem. In fact, for most cases, we're only going, in fact, for pretty much all the ones we are interested in, we're always going to pick a 4 well-separated decomposition. Going larger than 4 is usually unnecessary, right? For the closest pair, you can actually do it with a 2 well-separated pair decomposition. But we're going to use 4 for this algorithm, right? 4 is like the smallest number that will work. If you make it any smaller, it doesn't give you the right result. So OK. So that's the k nearest neighbors, or the k closest pair, k closest. All right. So the other algorithm, which I'm just going to write up here, right? It's actually a really, really simple algorithm, is the all nearest neighbors. So everyone OK with this? I'm going to erase it now. All right. So we'll do all nearest neighbors. All nearest. So what is the all nearest neighbors problem? It's the basic idea is we want to find some map f from P to P where f of P is the closest point, right? So we're going to think of F as basically finding the closest point in P not equal to P. So this is the argmin of all Q in capital P without P contained in it, basically P minus Q. All right, so this is, for every point, we want to locate its closest point, right? And this is not a symmetric relationship, right? So for example, if I have, like, say, 2 points here, these might be closest, but then I put another point way over here. This guy's closest point is now over there, right? So this is not like, some easy symmetric function. It's, just a general thing, right? So I'm going to give you the algorithm, and it's really just one line once you already have your well-separated pair decomposition. But it's a little subtle, right? So we're going to say, here's the algorithm. Which is basically compute W, which is equal to a 4 well-separated pair decomposition of P. For every pair of the form P and U, right? So basically where we have a singleton element in one of the elements of the well-separated pair, set f of P equal to the argmin of f of P and then the closest point in U, right? So we'll basically look for all of the Q's in U, P minus Q. So that's the idea, right? You basically construct this well-separated pair decomposition. Now, the first point is it's not, or I think we talked about it briefly last time, but once you build this thing, if you have a 4 well-separated pair decomposition, then there's always going to be some pairs which will have singleton elements. So every point in your initial point set will be contained in at least one singleton pair at the end of the day. So the claim is that you only need to look in these singleton pairs. And that this will actually work is not so hard to see, right? Because, right, so this is the algorithm. So to check that this works, right, I'm going to make the following sort of lemma here, which is...
Can you kind of explain a little bit the whole, like, so f of p is argmin of f of p?
Yeah, f of p, think of it this way, right? We'll think of f of p equals closest point in P not equal to P. That's what it means, right? So we're basically searching over all of these Q's, right, which are in P. If we take away little p, and we compute their distance, whichever one is the closest, that's the Q that becomes f of P.
Yeah, I understand it when you're defining the map. I was in the algorithm. I'm not sure.
Yeah, so we'll basically initialize f of p to some arbitrary random point not equal to p. All right, whatever, right? And then we just go through and loop through for each of these pairs. We just search over all of the pairs p cross u, right? So in other words, basically another way of thinking about this is that the closest f of p is in the union of all of these pairs p cross u, right? So if I look over all of these pairs where p appears as a singleton element, then I'm just going to search through each of those, right? That's the idea. So I'm only going to look in the ones where p shows up by itself. That's it. I don't have to worry about the ones where p shows up grouped with a bunch of other elements. I can disregard those.
And you're looking at the set U to try to find...
Yeah, exactly. So U is a set of points, right? It doesn't include p. It's its own set of points. When I do the search, I just get to the point p, and then I search in the set U for the closest point to p so far. There might be multiple points like this, right? So there could be multiple pairs that have p as a singleton. I have to look at all of those singleton pairs and then check each of them against P. That's the idea. So here's the idea. All right, so here's the concept. So we'll say this is why this works. All right, so let U of V be a pair where P is in U, and the closest point to P, that's f of P, is in V. Then U is equal to a singleton. All right, this will, if we can prove this lemma, right, then this algorithm is obviously correct. All right. So here's our proof. All right. So we know that the diameter of U is less than or equal to 1 over 4 times the distance from U to V, right? Which is our hypothesis here, right? That's just, because it's well separated. And this again has to be less than or equal to 1 over 4 times P minus f of P. Well, okay. If it's less than or equal to P minus the closest point of P, right, divided by 4, well then this, the diameter of this thing, right, there has to be at least some point inside here, right? If it was not 0, that would make it like larger. But if that was the case, then the closest point to P, f of P, would have to be contained inside U, right? So therefore, U doesn't contain any other points besides P, right? That's the idea. So U has to be a singleton. So it's just simple one-line direct calculation from the definition here, right? So we're all good? OK. So that means that this algorithm will work, right? We will eventually find the closest pair of points for each of these things because we have a 1 over 4 well-separated pair decomposition. Again, the parameter 4 is crucial to making it work. So, OK. So that's the fact that it's correct. Now, the harder thing to show is that this will actually run pretty fast, right? And to do that, we have to argue that each of these sets U doesn't get too large. But we're kind of running low on time, and I don't want to and there's some other stuff I want to talk about. So suffice to say that you can show that each of these sets U will contain, or that each point inside this whole set of points will be contained inside one of these U's at most s to the d times. So even if you do have one of these things which is very large, the other ones will have to be smaller to compensate for it. So when you do this for all of the nearest neighbors, and you amortize it over this whole search, the total overhead of doing this search is order s to the d. Right? That's the key thing. So this will end up being not too big.
Isn't that kind of obvious, just with the fact that the size is s to the dn?
Well, no, because they could all be like large sets, right? So there are two related concepts here, right? One of them is that there's the total number of pairs here, and then the other one is that you have basically this other thing. So you can imagine, like, I mean, this won't actually happen, right, because of the construction, but
just like all that every
yeah, but
set every time.
the thing is, the basic point is that the argument is a little delicate, right? And I'm not going to do it right now because we don't have much time, and you can look it up on the internet, right? You can figure this out for yourself. So OK, that's good for now. So let's get to the other thing that I want to talk about, which is a faster way to build one of these fair split trees. So sort of the industrial grade fair split tree. And this will probably be the only point in this course where we're going to come across quad trees. So this will be an algorithm that uses a quad tree to build one of these things. That's slightly better than what you could do with, sort of this crazy brute force algorithm for building fair split trees. So, oh yeah, and then I should also point out a couple of other things too. There's a few things I wanted to mention. So one obvious thing is that you can use these well-separated pair decompositions to compute the diameter of a point set, or estimated at least, to a factor of like 1 plus 1 over s or something like that. You can also use it to build a Euclidean minimum spanning tree, where what you do is you actually use the pairs themselves to do that. So actually, like the fast algorithms for computing approximate Euclidean minimum spanning trees all rely on this.
Is it in debug at all?
No, none of this is in debug.
So.
No, this is all independent from de Burgh, right? So this is not in there. Right. So okay, so let's go now to the one kind of interesting use for a quad tree, right? So this will seem at first like a slight diversion from this, but we'll bring it back here. So this is our sort of industrial kind of fair split tree, right? The easy fair split tree. This is not the best algorithm for building fair split trees, but it is the easiest algorithm that is subquadratic. And it uses a thing called a quad tree. So the basic idea in a quad tree, and I'm going to use this to collectively refer to even the higher dimensional versions of this. So we're going to say it's also called octrees or whatever. I mean, the generalization to n dimensions or d dimensions is straightforward. We're not going to worry too much about it. So we're just going to recursively subdivide a unit cube. Right, so this will basically be the interval 0, 1 to the d into 2 to the d hypercubes of equal size. That's the concept. So here's sort of a picture. So I'm going to start with the unit square, right? So this is basically the unit square from 0 to 1, 0 to 1. By the way, we're going to assume that all of our points live in this unit square, right? So if they don't, you just have to rescale them, by some, like unit factor or whatever, and then stick them in the square, because we're not going to deal with like completely unbounded point sets. And so imagine we have a collection of points. And so the idea in a quad tree is that we're going to recursively chop this thing into quadrants, right? In 2D, there'll be quadrants. In higher dimensions, there would be octants or, I don't know, sextants or something like that. Who knows? And you just keep doing this until each of these points, or maybe some constant number of points, is stored in some final grid cell at the bottom of the quad tree. All right. So that's all well and good. There are a few things to note here. One is that the size of this thing is not really bounded. So the sort of immediate and obvious problem with this data structure is that if I take 2 points and put them together very, very close down here, then what will happen is I'll start subdividing, and I'll start subdividing, and I'll keep subdividing. And it'll eventually just keep going, over and over until eventually I've built some like really, really fine quad tree, right? So the number of levels in this thing could be extremely large. All right, so the first point is that the size or height is independent of n.
It's still technically like logarithmic in the precision.
Yeah, so we'll get to this. We'll get to this, right? So there is a way in which you can make this precise. I think people are queuing to try to get in there, but I want to just go through this very quickly. So, okay. Instead, we're going to define this new quantity, which we're going to call the spread, and we'll write it as phi. So phi is equal to the diameter of our point set divided by the resolution of our point set, where the resolution of the point set is basically the distance between the closest pair. And this is called the spread. So here is the main sort of result of the quad tree. The height of a quad tree is order log of the spread, and size is order n times log phi. So you can sort of think of this spread factor here as acting as some stand-in for n, right? The main problem, though, is that in general, log phi is strictly larger than log n, right? So so when we do algorithms using quad trees, we'll basically get some time complexity that looks like order n log phi, which is, okay, maybe not stellar, right? But if our points are uniform, right, which is sort of the optimal case for this, right? So basically the closest pair of points aren't too close together, then log phi is a roughly log n, right? And so what we will see now is how we can use quad trees to build a sort of approximation to a fair split tree in n log phi time, so n log of the spread. All right. And the way that we'll do it is, can I quickly get the time here? 2:17. OK. Yeah, we'll just have to do this next time. I'm sorry. I kind of messed up the timing here. So it looks like there's a bunch of people outside, so we'll just have to call it quits. But suffice to say, we will see how we can use quad trees to build a pretty reasonable approximation to fair split trees relatively quickly.
I guess it's not pseudoscience after.
Well, this is the only thing they're good for.